Hello. I've gotten a lot of mileage out of this slide. I like it because of the potential links between our recent marine heat wave off the west coast of North America and global warming. I also think it's kind of interesting how it was published from a newspaper in that hotbed of environmental activism known as Utah. Today I'm going to talk about what is a marine heat wave, a fair amount about this recent one off the west coast, briefly about subsurface marine heat waves and the impacts on the weather, the prediction of them, and finally all this in the context of climate change. All right, Alistair Hobday formally defined marine heat waves as periods when the ocean is warmer above a threshold for long enough. In his original definition, they had to be longer than 5 days. In most applications now, it's even longer than that. But let's go on and look into the recent one off the West Coast. And my interest really started in the winter of 2013-14 when I noticed there was just a persistent ridge of higher than normal pressure off the coast of the Pacific Northwest, as indicated in the sea level pressure anomaly map. That high pressure blocked the usual parade of storms. There was less wind drawing heat out of the ocean and stirring up the upper part of the ocean and thereby getting cooler water from below up into near the surface. And as a consequence, the ocean got considerably warmer than normal off our coast by early 2014. This may not seem like a big deal to you, but when you look at a record going back to 1900 or so, sure, there's lots of year-to-year and multi-year variability and a slow warming trend, but there the blob of 2014-16 really stands out as kind of uncharted territory. And what's kind of interesting is we have another fairly sizable event has just occurred in the last year also. Again, this is for a box about 1,000 kilometers on the side off our coast. A recent PhD graduate of the University of Washington done a very careful study of both the marine heat wave of 14-16 and marine heat waves elsewhere in the global ocean. And so I want to share some of her results with you. Here for this box indicated in the upper left, it just shows the time series on the right there of where the temperatures for that box exceeded the 1 standard deviation threshold over that period from 2013 through 2016. And so this marine heat wave, it waxed and waned a little bit, but it lasted a long time. She did a careful study of the heat budget for the mixed layer of the upper ocean, and in particular looked at the terms impacting the temperature tendency. And from left to right, on the right side of this equation is the surface heating, the net surface heat fluxes, the air-sea interface, the horizontal advection, and then finally a complicated term representing entrainment and diffusion at the base of the mixed layer. And the effects of the cooler water that's below that mixed layer, how much of that gets into the mixed layer. All right, so over the course of this event, what's plotted here, apologies for slightly small plots, but want to put them all in one figure. It was relative to the normal for that area and time of year. The reddish color is showing where there's a warming effect, or the temperatures changes with time are greater than usual. In blue, just the reverse. What we can see is, yeah, sure enough, there was warming relative to the seasonal cycle early in the period. And on the upper right, you can see that to a large extent that was due to the net heat fluxes at the surface. The horizontal advection early on played at times a minimal role, but overall wasn't a huge um, impact. The bottom processes that were calculated as a residual at times were very important as deduced, but there were times also that obviously it was causing cooling of that area. Now, about those net surface heat fluxes, something that I think is kind of interesting is if you step back a bit, once you get the ocean warm, it's naturally going to radiate more long wave radiation to space, and so you're going to be cooling due to that. It's also going to promote greater sensible and latent heat fluxes out of the ocean if the atmosphere is in its usual state, just the ocean being warmer. But what happened during the blob for its kind of maintenance phase was that those fluxes, the net heat fluxes overall, were close to neutral, and that was because of what happened to the clouds. What happened was the atmosphere responded to the ocean forcing by having fewer clouds, and especially fewer low clouds. More sunlight was able to get to the ocean surface than usual, and was a heating effect. And so in essence, the fluxes were kind of a wash, and just they did not dissipate the heat wave once it was formed as much as you might otherwise think. The same sort of thing she found was for the combining the onset and maintenance phases of marine heat waves in the world's oceans, looking at the various terms responsible for them. Again, the upper left, you can see the upward long wave radiative flux during these events. The ocean's warmer, so it's going to be a cooling effect. It's radiating more energy to space. But overall, a very important thing, what's shown in the lower left, is that the atmosphere responds, especially in the subtropics, with a decrease in cloud cover, more shortwave radiation getting to the surface, and then in the lower right, showing overall that in much of the world's oceans, the net heat fluxes act to maintain these events during them. The big exception there is in the equatorial Pacific, where there's the big blue color shows that the marine heat waves there, otherwise known as El Niños, it's oceanic processes that are maintaining them, in that the surface fluxes are acting to cool the ocean. So to keep it hot, the ocean has to be playing an important role. All right. But there's parts of the ocean that other things are going on, in particular along our coast, in the U.S. West Coast. There's that's a system that is prone to upwelling favorable winds, especially in the summer, when if you look at the lower figure in the center there, the mean pressure pattern, the clockwise winds around that high means upwelling along the coast. And the consequence is that, as shown in the example on the left, is cooler water right along the coast versus offshore. Well, if those winds that are causing that upwelling are temporarily interrupted, then the ocean responds pretty fast, and there can be temporary warming that can last a week or two, that enough to constitute, by many definitions, a marine heat wave. Another thing that occurs on the West Coast, both of North America and South America, are coastally trapped waves emanating out from lower latitudes, and their impacts on the mixed layer as these waves propagate poleward. And here's just an example from Chile showing that one of these coastally trapped waves resulting in temporarily higher sea level, and definitely a spike in temperature that lasts long enough that to constitute a marine heat wave. All right. want to briefly go over an example of a subsurface marine heat wave. These haven't gotten as much attention, but in many cases, I think they're pretty important because many of the important species, commercially important fishing, for example, live at depth. And so we need to know what's going on down there as well as at the surface. So for context for this example, just showing this figure showing the mean currents flow in the Gulf of Alaska, counterclockwise circulation. And here, kind of to contrast what happened just recently in 2019 with that in 2015 during the heyday of the blob. In 2019, overall, the mixed layer, as shown in this temperature profile versus depth, was less in the upper 50, 180 meters or whatever, but it's quite a bit warmer at depth versus 2015. So the surface and subsurface aren't necessarily tightly coupled. If we actually look into what was happening during that event, there was, if you look at the panels along the bottom there, in the summer of 2018, there was some warm water at depth. These are temperature anomalies at the 100 to 250 meter layer in the southeast coastal region of the Gulf of Alaska. During the winter, it really warmed up there due to, according to this ocean reanalysis, an offshore directed and downward flow there that locally brought some warmer water to this 100 to 250 meter layer. And then the mean circulation around the Gulf brought it into the Kodiak Island, where there's an important cod fishery. And some of that warm water at depth appears to be a kind of a lingering hangover from the blob. A careful study hasn't been done here, but various ocean reanalyses are suggesting that. Just how it got there, can't say right now. But again, I think this is something that we need to learn more about. And one of the things that hampers us in that regard is just the scarcity of subsurface temperature and other oceanic measurements in the shelf regions. Argo does a great job in the deep basin, but in the all-important shelf regions where a lot of our fish and other marine resources are, there's a lot less certainty about what's going on there. And so that's just a caveat in trying to figure out what's going on. All right, I want to spend a couple of minutes on just the weather impacts of marine heat waves. For the most part, especially the ones here in the kind of eastern oceans, they appear to have more of an impact on the thermodynamics of the atmosphere rather than pressure patterns and winds and so forth. And in particular, when it was really warm off our coast in the winter of 2014-15, that was certainly an important factor in bringing us some really warm winter temperatures that year and record low snowpack. I've done some very simple sort of work just looking at a correlation between an index for the sea surface temperature in the box off our coast and the kind of the blob region and air temperatures a couple of months later elsewhere and on the left, and humidity levels in the atmosphere a couple of months later. And what the results make a lot of sense that that impact of the ocean on the weather is felt mostly up to the kind of Pacific crest, to the kind of middle of Washington and Oregon, to the Cascades, and not so much inland. And that makes sense given our prevailing winds and just what affects the weather in different parts of the country. It turns out that a very simple statistical model based on just ENSO, the Nino 3.4 index, and what a regional SST off our coast, in this case, for predicting Washington spring temperatures, does a reasonable job, as shown as the scatter plot on the right. And so if we can forecast Nino 3.4 and the regional SST, then we probably have a good idea, at least sometimes a year, about what that's going to be like for our weather. And there is some indication that we do have some skill forecasting, especially ENSO. That's a whole different subject, but our ocean temperatures in some parts of the world's ocean basins, with the Northeast Pacific being one of those places where there's a little bit more predictability. And this is just an example on the upper left of a forecast from the CFS model out of NOAA with what was observed in the kind of lower right. It can't go into this into great detail, but a forecast system we've developed for the Pacific Northwest coastal region, JScope, the early indications are that we have somewhat more skill at forecasting properties at the ocean bottom than at the sea surface, where the complicating effects of the atmosphere are more directly felt. And that's kind of important. If you're a sardine, you probably care more about the sea surface temperature, but the crab care more about what's happening at the bottom, and we do a little bit better job there. All right, last few minutes here, I just want to put this all into a climate context. I suggested you take a look at this paper by Michael J. Cox and company. That an important point there is for that region shown in the upper left off the U.S. West Coast, that if you look at the time series there, our climate models are pretty consistent overall with the trends for that region. And moreover, the half a degree of warming there or so that's occurred in the last few decades is responsible for about 1/3 of the magnitude of the blob. And it wouldn't have been as extreme an event if it hadn't been that background warming, and essentially a shift in the PDF of the SST anomaly distribution is shown in the lower left. And as we continue to warm, that's going to mean many more marine heat waves. And that's especially relative to land-based heat waves because it's such a narrow distribution of heat waves or of sea surface temperatures for the ocean relative to the variability in atmospheric temperatures over land. And so it doesn't take much of a shift in the PDF there to suddenly have a lot more frequent marine heat waves relative to historical norms. A few of us have also been looking at climate change and what. All right, so for just kind of setting the stage for some questions afterwards here. Some work has gone on, but I think there's plenty to do about looking more at about how marine heat waves, their mechanisms vary with location and season and versus the onset and maintenance phase. Again, not much has been done on subsurface marine heat waves. Almost nothing on marine cold snaps. Are they the mirror image of marine heat waves? We don't know. And I would argue that by trying to do predictions of marine heat waves on an operational basis, we're going to learn about what we need to do to monitor them, what mechanisms are really responsible, and by doing that sort of thing, we'll be better poised to kind of deal with the marine heat waves that are certainly going to be part of our future. So with that, thanks. What it means for the variability in the sea surface temperatures, and I've done some work in Alaskan waters. Michael Alexander and company have done elsewhere that have suggested that when you look in the model climatology to first order, the changes in the variability aren't very prominent. There's some indication that maybe in the summertime that there's going to be somewhat greater frequency of extreme events, but for the most part, it's a shift in the mean temperatures. That still means a lot more marine heat waves relative to when the threshold is based on historical norms, but it's not like there's going to be a lot more. The standard deviation is necessarily going to go up much, if any.